Today we're going to learn how to add up the numbers in a geometric sequence and find the grand total. So how do we find the sum of a geometric series? In the previous video about arithmetic series, I suggested 4 different strategies. One strategy is you might be able to just write it out if it's not that big of a sum, or you could use the Gauss method. You could put it in sigma notation, or you could use some sort of a formula. Let's see if those work. So here's an example. Find the sum of the first 8 terms of the sequence, 1 plus 3 plus 9 and so forth. It's a small enough sequence. Writing it out certainly would not be that hard, but it wouldn't teach us anything either. So let's try to use the Gauss method on it. Remember, Gauss's technique was to take this series of numbers and write it in reverse. By the way, spoiler, if you're somebody who doesn't like it when things don't work, don't write this down. So let's write it backwards a moment. If we write it backwards, we've got here 1 plus 2187 is 2188. And then the next one is wait a minute, it's not 2188. And then the next one's not 2188 either. So that's what was so magical about the Gauss technique, is that every time we added these things up, they always matched. And so you could count how many of columns there were and simply multiply. That doesn't work for a geometric series. However, we're not completely lost. There's a variation on the Gauss technique that's kind of cool that I want to show you. The variation says, instead of simply writing that sequence backwards, I'm going to take this sequence of numbers and I'm going to multiply it by what the common ratio is. And so from here, this is 1 times 3 is 3 times 3 is 9 and so forth. So I would like to take this sequence and multiply it by 3. If you do that, 1 times 3 is 3, and 3 times 3 is 9, and 9 times 3 is 27. And so you end up getting the same sort of numbers. But then this last one, 2187 times 3, gives us 6,561. And so there's a lot of numbers in common here. And what I'd like to do is I'd like to subtract them. Let me rearrange this a little bit. Let me take 3s and let me subtract 1s from it. If I do that, 3s minus 1s, of course, is 2 s's. And 0 minus 1 is a negative 1. And look what happens to all these terms. 3 minus 3 is nothing. 9 minus 9 is nothing. 27 minus 27 is nothing. And the vast majority of these terms are going to end up subtracting away. But then that last term at the end, 6,561 minus nothing, is, of course, 6,561. And so in this case, most of those terms canceled out, and I've got something that's really easy to do. 6,561 minus 1 is 6,560. And that is, of course, what 2 times our series is. And so if we want to know what our series adds up to, we simply need to divide by 2. And so our sequence, in this case, is whatever 6,560 divided by 2 is. So this technique, where all of the terms in the middle cancel out and they leave behind just the first and the last term, that's called a telescoping technique. It's called that because of the old school pirate telescopes that would collapse in on themselves. Hey, look, it's collapsed in on itself. It reminds me of a joke. Do you know what a pirate's favorite part about geometric series is? It's the ratio. All right, I'm sorry, we'll move on. All right, so why don't we try that technique on a general sequence and see if we can come up with a formula that should work for all problems. Remember in the last problem, we multiplied by the common ratio, which was 3. And so let's do that again here. If we multiply the sequence by r, then a times r would become ar. And AR times R would become AR squared, and then AR cubed, and all that sort of stuff. This term, if we multiply it by r, should give us a times r to the n. And so here is r times r sequence. Notice most of those terms are the same, but now we've got one more at the end, and we don't have that one at the beginning. Then remember, we subtracted these. And so let's take a look at what that would look like when we subtract them. If we have r of them and we take away one of them, then now we have r minus 1 of our sequence. 0 minus a would give us a negative a. And the vast majority of these terms in the middle cancel out. And we've got an a times r to the n at the end, minus nothing is 0. So here is what that total is. I'm going to clean that up just a little bit. I'm going to write this as a r to the n minus 1a, or just minus a. And if we divide both sides by r minus 1 and factor out the a, we end up with this particular formula. So the sum of a geometric series, this is a great one to memorize, and by the way, is the first number in the list times r to the n minus 1 on top of r minus 1. All right, so now that we've taken a closer look at a particular problem, let's update how we can find the sum of a geometric series. First of all, writing it out, not always a bad idea. If there's only 8 terms, it would have been a lot faster than watching this stupid video, huh? The Gauss technique didn't work, but a variation of it, the telescoping technique, that worked. Sigma notation is always an option. Haven't tried that yet, but we will in a second. And we could also use a formula. And there's a new formula now for the geometric series, which remembers the first number in the list times this fraction containing our ratios raised to some powers. All right, now it's time to see it in action. Let's find the sum of the first 10 terms in this sequence. In this sequence, we are starting with 16, and then we're taking away 48, and then adding 144, and taking away 432. Let me rewrite this a moment, so make it more obvious that this is a sum. We are starting with 16, and then we're adding a negative 48, and then adding 144, and then adding a negative 432. And the numbers in this sequence are a geometric series. We are multiplying by negative 3 each time. 16 times 3 is 48, times 3 is 144, and to get the alternating signs, we have to put that negative in. So let's use that new formula and calculate what our total is. Here's the formula, and to write this in, our total is equal to the first number in the list, which is 16, and then we're going to need to multiply that by what our ratio was, raised to the nth minus 1, over what our ratio is, minus 1. And so our ratio was negative 3, and I'm going to raise that to n. I want 10 terms, and so I'm going to raise that to the 10th power on top, minus 1. And then I'm going to divide that by our common ratio, which was negative 3 minus 1 on the bottom. Now, lots of cleaning up can be done here. So let's see. On top, negative 3 to the 10th minus 1 is a huge number. That's 5,900. I'm sorry, that's 59,049 on top, minus 1. Then down the bottom here, negative 3 minus 1, that's negative 4. And 59,049 minus 1 is 59,048. And if we divide that by negative 4 and multiply that by 16, we get our total. That total was 236,192 negative. And let's just check and see if that makes a little bit of sense. We start off with something positive, and then we take away more, and then we add a little bit more positive, but then we take away even more. And so the 10th term in this would have been a subtraction problem, and so we would have subtracted a lot. And so I think that makes sense that we should have a big negative number here. Of course, we can always find this using a different technique. And so why don't we try using the sigma notation for it. To use sigma notation, remember we need a formula for the nth term, and then we need down here probably n equals 1 to 10, because we're going 10 terms. And so the formula for a geometric sequence is the first number in the list, which was 16, and then times the ratio, which was -3, and then we want to raise that to the n minus first power. On a calculator, you'll have to be pretty careful typing that in. Make sure you put the -3 in its own set of parentheses and the n minus 1 in a set of parentheses. As a reminder, to calculate that, we need to use the sum of sequence command. So the sequence command takes our function, which is in this case 16 times times -3 raised to the n minus 1. Our variable we chose to use was n. We chose to start at 1 and go to 10. And so if you were to type that into your calculator, that should give us that negative 236,192 number. We can also use a spreadsheet to find this, and so why don't we try that? So this will be a little bit more complicated than the last time we used a spreadsheet, but I think you'll be able to follow it. So I'm going to have two columns here. In the first column, I'm just going to have these numbers, 16, -48, and so forth. And so we'll do that by typing a 16 in, and then using a formula. Remember, the formula is to take the last number and multiply it by -3. And I'll drag that formula down a couple times here. I need to go 10 terms into the sequence, so we'll stop there. And then over here, I'm going to create a running total. And so I'll do that by starting off with just 16. And then each time I'm going to take this, what I had before, and add the next term. And so I'll do an equal sign. And this first, what I had last time, and I'm going to add to it this new item. And so 16 plus -48 is -32. And if I drag that formula down here, you'll notice after 10 terms, we've got our -236,192. So one last type of question. This one asks how many terms are needed to reach at least 1,000,000. And so I would encourage you to try to pause it right now and see if you can find it on your own, and then come back in a second and see how I did it. I'm going to use that same technique we did last time and just kind of look at a table. And so to do that, I'll start with a 6, and then the ratio in this is multiplying by 2 each time. And so I'll take this value and multiply by 2. If I drag that down, eventually these numbers get fairly big. Remember, I'm not interested in when these numbers get to 1,000,000, but I want to know when the total gets to 1,000,000. So I'm going to create a running total here like we did last time. I'll start by just saying it's equal to this, and then each one of these boxes is going to be equal to this box plus the box next to it. And I'll drag that down, and this is what I want to know. When does this column reach 1,000,000? And it looks like, still not there yet. Maybe one more. Yeah, so it looks like after 18 terms, I've passed 1,000,000. Suppose you don't have a spreadsheet handy and you'd like to be able to calculate it a different way. We could use the geometric series formula to help us. And so as a reminder, the geometric series formula is the first number in the list times that fraction, which is the common ratio raised to the nth minus 1 on top, divided by the common ratio minus 1 on the bottom. If we start to fill in some of the things that we know here, I know that S is 1,000,000, and I know the first number in our list is 6, the common ratio, 6 times 2 is 12, times 2 is 24. So I can write a 2 in here and a 2 in here. And now I've got some work to do. This is not an easy equation to solve. I will begin by just cleaning up the left-hand side, this or right-hand side. That's 1, which is really nice because dividing by 1 just goes away. And then I want to divide both sides by 6. If I divide both sides by 6, that leaves behind just 2 to the n minus 1 on that side. And 1,000,000 divided by 6 is 166,666. Now I'd like to get rid of that minus 1, and so I'll add a 1 to both sides. And that gives me 166,667. And to finish this, you'll have to use a logarithm. What I'd really like to do is take log base 2 of both sides. Log base 2 isn't built into your calculator, so you're going to have to use the change in base formula. To type that in on most calculators, you'll have to type in log of 166,667 divided by log of 2. And so let me take that and type it into my calculator a moment. And that gives me a 17.34 number, which makes sense. That was how many terms, right? It was after 17, but not quite 18 terms is how many we would need. So we'd probably round that 17 point something number up. Anyhow, there is a handful of different ways that you can calculate geometric series and some variations on it. Good luck solving things. Let me know if you have any questions, and I'll be glad to help. And tune back in for the next video. Have a great day.